talk about chapter 3.1, which is all about solids, liquids, and gases. And I know that you guys have learned a lot about these three things already, but hopefully what we learn over the next week or two will extend what you already know. But to kind of review, materials can be classified as solids, liquids, and gases based on whether their shapes and volumes are definite or variable. So, depending on whether an object has its own shape or its own volume, we can determine if it's a liquid, a gas, or a solid. So in this background here, it turns out we have two different states of matter. We have both liquid and gas. The gas is in the sky, which is the blue part of this whole background, and the liquids are the clouds. And the clouds, you can see, are all clumped together, whereas the gas is all over the place. And that is pretty indicative of how we will define liquids, gases, and solids. So a solid is the state of matter in which materials have a definite shape and a definite volume. This means that a solid always has the same shape unless you make a physical change to it. An example is these blocks right here inside this container. When we put the blocks in the container, they do not move to take the shape of the container. They keep their rectangular shape. And the particles inside a solid are really, really closely packed together, like in this picture. They're not moving around or going from one place to another. They stay where they are, which is what helps it keep its definite shape. It also has a definite volume, meaning we cannot squish it to be more compact or pull it apart to make it less compact without causing a physical change to it. Liquid is the state of matter in which a material has a definite volume, but not a definite shape. So you can see by this picture here that this liquid would fill all of these different shaped containers. It can take on the shape of whatever container it's in, but the volume will stay the same. That means a liquid is not compressible. We can't compress a liquid and make it more dense than it is, and we can't stretch it out and make it less dense than it is without causing a physical change. So if I start with 100 milliliters of water and I pour my 100 milliliters into each of these bottles, the shape would change, but the volume would still be 100 milliliters in each and every one of these because the volume will not change. And gas is the state of matter in which a material has neither a fixed shape nor a fixed volume. So a gas can take the shape of whatever thing it's in, for example, a balloon, and as the balloon grows, because more gas is put in, the shape will change over time. And you can change the volume of a gas. You can compress a gas, or you can stretch it out and make it less dense. There are two other states of matter in the universe that we know of right now. Plasma is a fourth state of matter that actually makes up about 99% of the matter in the universe. It's not as common on Earth, but in the universe, talking about clouds and nebulas and stars, all of those are made out of plasma. And we're going to talk about what plasma is a little bit tomorrow. And the Bose-Einstein condensate is a really bizarre fifth state of matter that was actually just recently confirmed about 20 years ago. Now 20 years may seem like a long time for you guys, but that is really, really recent, especially since Einstein himself came up with the theory that this state of matter existed back in like the 40s or 50s. So it took about 40 years for them to confirm that this state of matter actually exists. Now, the three main states of matter can also be described by something called the kinetic theory. And the kinetic theory of matter says, not said, says, that all particles of matter are in constant motion. Now, in physics, we talk about something called kinetic energy. And kinetic energy literally is the energy of motion. So the faster something is going, the more kinetic energy it has, depending on its mass. That means if you are driving in a car and you're speeding, you're going 20 miles per hour above the speed limit, you have much more kinetic energy than you're supposed to, and you're going to get pulled over. Now, the kinetic energy of the particles inside different states of matter can help us define them. For example, the kinetic theory for gas tells us that the particles in a gas are in constant random motion, and this constant motion allows a gas to fill the container of any size or shape. So the particles are constantly zooming around very, very quickly. They have a lot of kinetic energy. And they're moving all over the place in a totally random pattern. And as they move around, they bump into the sides of whatever container they're in. If we're thinking about the balloon, those particles are constantly bumping into the sides of the balloon. And that's what causes that balloon to stay inflated, is the little bumps between the particles and the balloon. And the motion of one particle is unaffected by the motion of another particle, unless they collide. And this actually doesn't happen that often because the particles in a gas are very far apart. Now, every once in a while, they will bounce into each other, but then they just bounce off and keep moving. But 90% of the time, the motion of each particle is totally unaffected by the other particles. It's like they're not even there. It's like they're the only particles in that container. And the forces of attraction among the particles in a gas can be ignored under ordinary conditions. Now, this is pretty important because it turns out all mass, all matter, has an attractive force between all other matter. So particles inside any kind of state of matter are always attracted to each other. But in a gas, these particles are moving so fast and so far apart that those forces of attraction are basically zero. So scientists just kind of ignore them. Now let's apply all of this to a little bit of a picture. So we have a little beaker of water, and I'm going to heat it up to 100 degrees Celsius. And you can see this is what gas particles look like. They're bouncing all over the place, moving very quickly, hitting the sides of this container. And as they hit the sides of that container, that is what causes that container to take on that shape if it's a flexible thing like a balloon. This is why a gas can take the shape and volume of whatever container it's in, is because these particles are always bouncing around and hitting the edges. Now let's talk about liquids. A liquid takes the shape of its container because the particles in a liquid can flow to new locations. So that means the particles in a liquid are always moving, and they're always moving fairly quickly, and they can always move from one place to another. But the volume of a liquid is kept constant because the forces of attraction keep the particles close together. So liquid particles are like gas particles in that they can move from one place to another, no problem. And they're always bouncing into each other. But the particles in a liquid are different from those in a gas because the particles are much, much closer together. The forces of attraction between those particles actually keep them together and actually play a really important role in a liquid. So now if we cool our liquid down to about room temperature, which is like 37 degrees Celsius, you can see our particles have slowed down a little. They're still able to move from one place to another with no problem, but they're staying much, much closer to each other. And that's because those forces of attraction keep them very, very close, don't allow them to get too far away. Because the particles are so close already, that means we really can't change the volume of this thing. The shape is constantly changing, and you can see that as the particles move around. But the volume doesn't really change. The volume cannot be compressed, and we can't really expand it without causing a physical change. And finally, a solid. A solid has a definite volume and shape because the particles in a solid vibrate around fixed locations. So, the particles in a solid are kind of like the particles in a liquid in that the forces of attraction are very strong and keep those particles close together. But a solid is different from a liquid and a gas because the particles have to stay in one place. Those forces of attraction are so strong, the particles can't move from one place to another. They stay in one place and just kind of vibrate around. It's like they had too much coffee that morning and they're just kind of shaking. So the kinetic energy of a solid particle is much, much less than the kinetic energy of a gas particle. And we can see that with our little visual here. When I cool it down to make ice, solid water, you can see that the particles are now not really moving. In reality, these particles would be jostling around a little bit, kind of vibrating, but they do not move from one place to another. They stay in one place. This is why a solid has a definite shape, because the particles aren't moving around, and it's why it has a definite volume, because we can't compress this, and we can't expand it without undergoing a physical change, like melting it into a liquid. So, when you kind of sum all of this up, keep in mind the amount of kinetic energy the particles have. Gas particles have a ton of kinetic energy. They're moving very, very fast and far apart from each other. The particles in a liquid have about medium kinetic energy. They're moving at a moderate speed, but they're very close to each other. They're just kind of slipping and sliding around each other. And the particles in a solid have a pretty low kinetic energy. They're not moving very much, and they're very, very packed together.